Hello students. Next, let us look at some of the examples of Lagrangian formulation for 1 degree of freedom manipulator. DOF means 1 degree of manipulator. 1 degree of manipulator means we are talking about just one link attached to one joint. That will give only 1 degree of freedom. In your syllabus itself, it is written that Lagrangian formulation only for 1 degree of freedom needs to be done. So that is what we are going to do. Now the first we will take first example for the case of a revolute joint. Then we will look for the case of a revolute joint wherein there is a motor which is having a gear system. And next we will look into a prismatic joint. So these are the three examples that I wish to take. The first example is a 1 degree of freedom revolute joint. As you can see, there is a revolute joint that is drawn here in the center, and there is an axis x and y based on which we are trying to find the position of the mass m. Not find the position of the mass, we are just trying to define where the mass is, and the position of the mass is going to be decided by the value theta that is here. Okay, the theta, the angle with respect to x, that theta is going to decide what is going to be the position of the mass. Now here the link, generally the link is having a length of L and the link would generally have a mass, but for the case of simplicity we are considering that the whole mass is concentrated here in this particular point, and that's why we are calling it as a point mass, where the whole mass is concentrated. And what we are interested in is to find out what will be the torque in the direction of theta, so that we will be able to understand how much torque the revolute joint will have to provide so that the mass is moved in a theta angle. Okay, so as we have to do is, first we have to find out the energies. The energies, that is, first is the kinetic energy, which is K, and K is basically half of mass into velocity with which it is moving. Now the velocity that I am having is basically angular velocity, so I will name it not as V, I will have to name it as with respect to theta. So angular velocity means I will have to talk about omega. Okay, it's not omega also, basically it is rate of change of theta. So let me write that. Now generally the kinetic energy is written like this, but for the case of revolute joint, or for the case of a revolving mass, the velocity is basically given by the length of the link, okay, the length of the link and the angle. So basically I will be able to write the velocity as L theta dot, L theta dot the whole square. So why we are writing the velocity? See, if I am going to move away from the center, if the mass is suppose here, then the angle with which it is going to move, basically the arc with which it is going to move, is going to be L theta. Whereas if suppose the mass is not here and the mass is going to be here, at that time the arc that is going to be, the arc that is going to be drawn, it's going to be of more length. Why? Because the L has now increased from this small value to this complete big value L, the complete long value L. So the arc length is basically changing, because of which the velocity is going to also change. Because just imagine the time that is taken by this theta, the time that is taken by theta to basically go from here to here is same as when going from here to here. And here the arc length is more. See, this length is more than this length. So what can we say? We can say that as the value of L increases, the velocity will basically increase, and that is what we have got here. Okay, so let me run this one. Okay, so now the kinetic energy of the mass is known. Let me open up the bracket. So it is going to be half m L square theta dot square, where what is theta dot? Theta dot is basically the rate of change of theta with respect to time. So theta dot is d by dt of theta. Okay, it's already something that we have already discussed. Okay, next we will look at what is the potential energy. The potential energy P is going to be mg into the height, mgh. H is the height. So if this dotted line is going to be the height, and if this is theta and this is L, if the link is having a length L, then this will be L sine theta. So the height is going to be L sine theta. So I will write the height as L sine theta. So that is what is going to be our potential energy. You know that potential energy basically changes with respect to height. Okay. Therefore, now I can write the Lagrangian. Therefore, the Lagrangian L is basically the kinetic energy minus the potential energy, which is basically half m L square theta dot square minus mg L sine theta. So let me shift this whole equation so that I get a little bit more space there. Yeah, so this is going to be mg L sine theta. Okay, so now we have got the Lagrangian, and once we get the Lagrangian using the formula that we have already seen here, we can write the torque, isn't it? We can write the torque using this formula, but first for that I have to differentiate, partial differentiation. Okay, so I am going to first differentiate L with respect to theta. Therefore, tau is going to be d by dt of dou by dou theta dot of L minus dou by dou theta of L. So two things are to be calculated. One is what is dou by dou theta, sorry. First we have to calculate what is dou by dou theta dot of L, Lagrangian L. And what is that? So we have to differentiate this equation. So this is my Lagrangian, so I will write this as equation 1. So if I am going to differentiate equation 1 with respect to theta dot, so you can see the first term only has theta dot, the second term has theta, not theta dot. So for the first term, if I am going to differentiate, I will get half m L square, and theta dot, if I differentiate theta dot square, then I will get 2 theta dot minus the second term is having no theta dot term, so I will get it as 0, which now 2 and 2 will cancel, and I will get m L square theta dot. Correct? M L square theta dot. Next, if we are going to take the dou L by dou theta. So again, equation 1, if I would go, the first term, that is this term, will be totally 0. Why? Because there is no theta term, only theta dot term is there. Okay. So this one I will name it as 0, and the second one, the second term we are having with respect to theta, so that will be mgl. Instead of sine theta differentiation, we will get cos theta. So we are having the final value as minus mgl cos theta. Okay. Now, if I want to find out what is tau, then tau is basically the differentiation of dl by dt. So the first term I have to again differentiate with respect to time. So I will write here, and d by dt. So why I am writing that? Because here I am having d by dt. So d by dt of this term, which one? What we have just now found out, which is dl by d, not dl, dou L by dou theta, sorry. Dou L by dou theta. So dou L by dou theta dot, which we just now found out, is, once again I have to differentiate this one with respect to time. So m and L is having nothing with respect to time. That means the mass and the length is not changing with respect to time. Now what is changing is theta dot. So if I differentiate it with respect to time, it will become theta double dot. Correct? So now I am having this as the first term, the torque. So therefore the torque, so finally I have to write, so I will use a different color. So therefore from Lagrangian we get, therefore torque is equal to equation number 2 minus equation number 3. Correct? Equation number 2 minus equation number 3. So I will get this as m L square theta double dot minus of minus, which becomes plus, mgl cos theta. And that is what is the equation for this particular setup of a revolute joint. Okay, so as you can see here, it's a very simple thing. See what it is saying, that the torque has to be decided by two things. One is this part and the second one is this part, where this is just taking care of the acceleration. So here it is taking care of the acceleration part. Here it is taking care of the gravity. Okay. So the torque that is attached to this particular revolute joint, not the torque, the motor that is attached to this particular revolute joint, that should have at least this much torque if it has to move the mass m at an angle of theta with this acceleration theta double dot. Okay, which mass? The mass m, which is at a length of L from the center. This kind of an equation you will never get it, kinematic equation. That is what is the reason why we go for dynamic equations using the Lagrangian formulation. Okay, so this is one of the examples. We have to take another example. In the second example, we are having the link connected to a motor with a gear. It's simply like a revolute joint. The only thing is that here the motor is with a gear. And we all know what a gear system is. Just to show you a simple example, suppose if there is a smaller gear, okay, and there is another one which is bigger than that. Okay, let me draw it slightly more bigger. Okay, and suppose they are very close so that they are touching each other, and there will be teeth here, but I'm not going to draw the teeth. The only reason is that because it is going to take a lot of time. So suppose if both of them are touching like this and there are teeth in between, then suppose if the center, if I'm going to take the center of the first one is here, the center of the second one is here, okay, then the rotation of this will lead to the rotation of this in this direction. But the speed of rotation will be totally different for both of them. Here, if suppose the circumference here is suppose some value q, and here the circumference is suppose some value which is 10 times q, then it means that this one will have to rotate 10 times for this one to rotate once. That is a gear arrangement. Okay, what is a gear arrangement? You are having two gear sort of thing, wherein the rotation of this one, since it's the smaller one, this will have to rotate many times for the bigger one to rotate one time. Okay, and that ratio is basically given by this n is to 1. Okay, so if I am going to say that this is the motor and this is the gear, so the motor is going to rotate and the gear is going to rotate according to the rotations of the motor. Then if suppose the gear is having a ratio of n is to 1, it means that for n rotation of motor we will have one rotation of the gear. The gear arrangement is such that the bigger circle will have one rotation when we are having n number of rotations of the motor. In that case, suppose if I am going to consider the angle, okay, look at this carefully. Oh, sorry. If I am going to consider that I am having an angle, and that angle is, suppose for the case of motor, I am going to take theta m angle. So I will take this angle as theta m, and suppose this angle, if I am going to take the angle with which this is rotating, if I take this as theta l, okay, theta l, then what this means is that theta m and theta l will have a relation which looks like theta l will be theta m divided by n. Theta l will be theta m divided by n. Okay, this is something that we should not forget. So let me write that. I will move the other things. Okay, for a gear, okay, for a gear, gear system with gear ratio n is to 1, n is to 1, I should write it, n is to 1, the relationship that we are going to have is that theta L is going to be theta m divided by n. Let me put that in a small box where theta m is the angle of the motor. Theta m is angle of motor, and theta L is angle of link. Not linkages, it is link, L-I-N-K. Okay, so with this idea, now consider this system. So suppose you are having this motor, you are having motor and with gear. So motor with gear. Suppose you are having a motor with gear. Okay, if suppose you are having a motor with gear, and suppose this is the length L of the link. Okay, suppose this is length L of the link. Now let me do one thing. I will use a different L because I have used this theta L here. So let me write that also correctly so that it does not go as a mistake. So this should be theta small. Okay. So if suppose this length is capital L. Okay, capital L. Now the gravity is basically acting or pulling down. So initially suppose the mass was here connected to the link, and now the motor is running so that it produces an angular motion of theta, with which the m has basically come up to this much height. So what is basically going to be the height difference? The height difference is going to be basically this much. Okay, the height difference is going to be basically this much. This I will draw the other side. This, let me draw the other side with a different color. Okay, so this is the height difference that is going to come. This whole length is L. Similarly, this whole length also will be capital L. Okay, so it is basically, you can see this mass has swung from here and it has reached here. So it has basically acquired a potential energy, and obviously there is a kinetic energy. Now talking about the kinetic energy, look at here, this one very carefully. Here we will be interested in the two circles that we are having. Suppose the mass of the circle is going to be, the mass and the radius. With that we will get a moment of inertia. Suppose the moment of inertia of the circle that belongs to the motor, it is Jm, and the moment of inertia of the the gear, suppose if I am going to write it as Jl. Okay, and what is basically moment of inertia? It is mass into the length, the radius, mass into the radius square, Now here the mass is basically what is connected to the link. Okay, so here the gear, after the gear, the mass is going to be connected at the end of the link. So this is where the capital mass is, and this is what is total L is. Okay, I have drawn it slightly in a miniaturized form, so don't get confused. So suppose if that is the case, okay, then I can write my kinetic energy. The kinetic energy will be composed of two portions. First will be because of the motor, and second will be because of the link connected to the gear. Okay, and the one connected to the motor, I can write it as half Jm, where Jm is the moment of inertia, where I said it is mass into the radius. See, if you go to the previous problem, here we had written mass into L square. Remember this? Okay, that same is basically I can write it as J, which is moment of inertia, where L is how much far the mass was. So the case of motor, it is going to be the moment of inertia is Jm, and then theta m, which is the angular movement, and theta m dot is basically the velocity of with which the motor is rotating. And if I take the square of it, that will be the kinetic energy associated with the motor. And with respect to the gear, it will be half, and now instead of the Jm I will write Jl, which basically means gear and the link arrangement together, into theta L dot square. Okay, that is the kinetic energy associated with the gear system, and the link with the mass capital M. Okay, next, if I am going to look at the potential energy, which we'll basically write it as P, is now going to be mg. If you remember, it is mg and the height, and here the height was L sine theta, but here the height is basically this much. What is that height? What is going to be that height? Let us calculate. See, this is the total L, this is the total length L. Total length L divided by this much will be this. So what is this? This is basically, this can be basically written as L cos theta, correct? L cos theta. So this one comes out to be, let me write it here. This one comes out, this height difference, it comes out to be L minus L cos theta, which can be written as L into 1 minus cos theta. Okay, and so this will become mg, and the height difference is L 1 minus cos theta. Now what is this theta? This theta is basically theta L. Now if I have to write everything in terms of motor, then I can write this as mgl 1 minus cos theta m. You can take it from here, theta m by n, because that is what is the gear bringing into the system. Okay, so now what is going to be the Lagrangian? So therefore the Lagrangian is going to be capital L. So I will not write L because I have already taken it as the link length. So I will just write the Lagrangian. Okay, the Lagrangian is going to be this k minus p, okay, which comes out to be half. Now I can take half outside commonly. Similarly, here theta L, okay, I can write it as theta m by n, correct? So that theta m also can go outside, so I will write this as Jm, theta m dot I will take outside, plus Jl, half has gone outside. So this one I told you, this one is going to become theta dot m by n. So theta m I can take commonly outside, what remains is n square. That remains inside, and what we get outside is theta m dot plus mgl, this L is for the link length, okay, and 1 minus cos theta m by n. And now from or from the Lagrangian, we get from it, we get, what do we get? We get what is the torque. The torque, if you all remember, it was d by dt of dou L by dou theta m dot minus dou by dou theta m of L. So one by one we have to calculate what is dou L by dou theta m dot. Okay, if you look at the first term, so let me remove the unnecessary. Okay, so this is the equation. If you look at the first term, only has theta m dot. So the second term, differentiation is going to be 0. So what I will get is basically, so let me use a different color now. So now I will get dou L by dou theta m dot. Okay, so only the first term will be there. I have forgotten to write here square, sorry. So this is square. Okay, so if I am going to take the differentiation of that, what will I get? I will get 1 by 2, the remaining portion jm plus jl by n square. It's going to be as such. This one will give me 2 theta m dot minus, the second term is going to be 0, so I'm not going to write that. No need of writing 0. And what you can see here is 2 and 2 will basically cancel off. Therefore, I will just write, I'll cancel these off. Therefore, the term d by dt of this dou L by dou theta m dot, that means taking the time differentiation of whatever we are having here, I will simply get Jm, that is the moment of inertia of the motor, plus the moment of inertia of the link divided by n square, which is basically the gear ratio, and that multiplied with the 2 and 2 get cancelled. I will take only the differentiation of theta m, so I will get theta double differentiation, theta m double dot. And similarly, I will get for the second term, which is dou L by dou theta m, that if I am going to do, I will get, for the first time I will get 0 because it is only theta m dot. The second term m g l will remain as such. Okay, and the inside term, okay, so this was plus, the inside term is going to become minus, the cos becomes sine, and theta m by n, and finally, since it's with respect to theta m, that n will come outside, so I will get by n, which comes out to be m. I should not write small m, I should write capital M, sorry, here and all. Okay, if I have written, because I have written nothing, I have written small m for the motor, it is better to write capital M. So here it should be capital M, and here also capital M. Based on that, these values also should be capital M. Okay, so here it is going to be capital M, so it is m g l by n, and minus is going to come commonly, sine of theta m by. Therefore, combining them all together, I will get, so let me write it in a different color. Therefore, tau is going to be the first term, which is Jm plus Jl by n square theta m double dot minus of minus, which becomes plus capital M G L divided by n of sine theta m by n. And that I will now put in a box. So this is the dynamic equation which basically relates the position and the angular position of the motor and the angular acceleration of the motor with the mass, the moment of inertia, the gear ratio, the link of the link, all with tau. And what is tau? Tau is the amount of torque that has to be given by the motor so that the mass is lifted up, as it is shown here. And as I said previously, the kinematic equation will never give that. Only the dynamic equation will give that, and that is what is this formulation. Okay, so this was the second example. We will go for the third example, and this is basically a simple example. Again, here I am having 1 degree of freedom prismatic joint which is moving against the gravity. So the gravity is basically trying to pull it down. This is a prismatic joint, so here the movement is basically, it is trying to move up. Okay, so first things first, I want to find what is the kinetic energy. So I will write kinetic energy K is half mv square. Now what is the velocity here? Velocity is basically given by the position. Position is y. So the velocity is going to be half m, and velocity is going to be dot y dot square. Correct? And what is going to be the potential energy? The potential energy of the system is going to be P, which is mgh. Correct? If you remember, it was mgh. The potential energy is mg height, and the height is just whatever is the position here, which we are taking it as y. Okay, the potential energy. See, if this would not have been like this, and instead if suppose it would have been like this, that means the prismatic movement is in the x direction, then you can see that the height is going to be 0, so the potential energy for such a case will be 0. So in that case I will get the value of P as 0. Okay, but anyway, we are just going to take for one of the cases, which is the prismatic joint. It's having a y moment. See, if it is going to be in the x direction, remember the potential energy will be 0. That's all. Okay, so if this is the case, then the Lagrangian. Next is we have to find out the Lagrangian. Therefore, the Lagrangian is basically given as L is equal to K minus P, which is half m y dot square minus mgy. Okay, and now we know that force in Lagrangian is basically given by d by dt of dou by dou y dot of capital L minus dou by dou y of capital L, which is the Lagrangian. Okay, now why I have not written theta here? Because this is going to be the case of a prismatic joint, and prismatic joint does not have an angular movement, it has a linear movement. As you can see, the linear movement is basically moving like this. So we are trying to find out what is the force that has to be given here? What is the force that has to be given here if we want to lift that mass which is kept there with the help of this prismatic joint? So this is the equation. So straight away, as you know, we have to calculate. So we are straight away going to calculate. Let me use a different color. So dou L by dou Y dot, you all know that in the first equation I will get the first part is going to be half m 2 times y dot, correct, minus 0, which basically comes out to be 2 and 2 gets cancelled, and I will get y m y dot, correct. Therefore I will also get d by dt of dou by dou y of L. I will get it as the differentiation, time differentiation of this is going to be m y double dot. Instead of single dot, it's going to be double dot, which means it is double differentiated. And I will get dou L by dou y as, if you look, the first part of the equation will become 0. The second part I will get minus mg, which is minus, totally it's going to be minus mg. Therefore I can say, therefore we can say that the force is going to be m y double dot minus m minus and minus plus mg. And see, this is correct. In a way, you can see and understand that this is correct. See, what is the force? The first force that it has to overcome is because the force due to gravity, the pull due to gravity. That is, what is m into g? What is mass into gravity? It is weight. So whatever weight is there on the top of the robot, that has to be countered by this force. And the second is the mass has to move with an acceleration. So that force also has to be taken care of. So this much total force has to be sent or given by the prismatic joint for this one to basically move. So that is for the case of 1 degree of freedom prismatic joint, how using Lagrangian formula or method we find out the force that is going to be required. So this is the dynamic equation for this 1 degree of freedom prismatic joint. Thank you.